One of the most common problems we're going to face in our study of thermodynamics is calculating the pressure created by a column of fluid. We're going to run into this often, and we're going to need to calculate either the absolute pressure at the bottom of the column of fluid or perhaps the gauge pressure at the bottom of the column. So let's begin our study of pressure created by a column of fluid by solving a simple problem. What is the absolute pressure of water at the bottom of a lake that is 5 meters deep? We want to calculate the answer in both kilopascals and in bars. We'll take the atmospheric pressure as 101 kilopascals, the water density as 1,000 kilograms per cubic meter, and the acceleration of gravity is 9.807 meters per second squared. So here I've rewritten the given data, and here's an illustration of our problem. We're interested at the pressure at the bottom of the lake, which is just out of view here. And that pressure is created by this column of water above it. And then sitting on this column of water is the column of atmospheric air, where that pressure was given as 101 kilopascals. So we can say that the absolute pressure at the bottom of the lake is the sum of the pressure created by the column of water plus the pressure created by the atmosphere. Okay, we know the atmospheric pressure that was given. The pressure of water we can calculate by this standard equation, which we're going to use over and over. The pressure created by a column of water is the density of the fluid times the acceleration of gravity times the height of the column. So we can substitute rho GH for the pressure of the water. And so now the pressure at the bottom of the lake is rho GH, which is the pressure created by the water, plus the atmospheric pressure. Let's solve for this. The pressure at the bottom is the density of the water, 1,000 kilograms per cubic meter, times the acceleration of gravity, times the height of the column of water, which is 5 meters. And so we have this rather messy term right here, plus the pressure of the atmosphere, which is 101 kilopascals. Well, if we multiply this first term out, we're going to get the pressure at the bottom is 49,000 kilogram meters per second squared per square meter. Okay, well, we recognize this term as a Newton. So we've got 49,000 newtons per square meter, and we're adding to that 101 kilopascals. So we're going to simplify this further. We had a 49,000 newtons per square meter, and we need to convert that to kilopascals. Now we'll recognize that a newton per square meter is a pascal, and that there are 1,000 pascals in a kilopascal. So this term reduces to 49 kilopascal, and we're going to add to that the atmospheric pressure of 101 kilopascal, and that gives us a pressure at the bottom of the lake, an absolute pressure of the pressure of the water, 49 kilopascals, plus the pressure of the atmosphere acting on the surface of the water of 101 kilopascals. And so the pressure at the bottom of the lake, the absolute pressure is 150 kilopascals. To convert that to bar, we'll recognize that a kilopascal is 1,000 pascals, and that there are 10 to the 5th pascals in a bar. We can see that our kilopascal terms cancel, our pascal terms cancel, and we're left with the pressure at the bottom of the lake is 1.5 bar. Now, if we had been asked to calculate the gauge pressure at the bottom of the lake and not the absolute pressure, the solution would have been created only by the column of water, rho GH for the water, and would not have included the pressure of the atmosphere, because the pressure of the atmosphere would not only act on the surface of the water, it would also act on the pressure gauge. And we're going to talk about pressure gauges in a later lesson. But this is how we calculate absolute pressure.